So in this video, we're going to talk about the directional derivative of a scalar function from Rn to R. I'm going to focus on R3, of course. And I'm going to use the fact of the chain rule that we talked in our previous video. So if you haven't watched that one, it makes sense to go back and watch that one before this one. So what the directional derivative measures, I'm saying that at a point x. So the directional derivative has to have a direction of u. So what we're talking about is we're going to have function from R into R. So pretend in my example n is 2. So this is my domain, my down here. And my output is this z-axis. And we visualize this like having a surface up here on top of my domain, and I'm going to grab a point x. That's going to be my point AB. So that means A in the x and B on the y. So this is my point x somewhere down here. And I'm going to think of the value of that function on that point gives me a point up here in the surface. So I'm going to have a unit vector u. So let me copy this for now and use this picture over here. So let me copy it. What the idea is, I'm going to have a unit vector u. So from here, I'm going to move in a certain direction u. And I'm going to evaluate what happens as I move along that direction up here in this surface. If you move up here in that direction, you will see a curve. I don't know what that curve looks like, right? And what it measures is the rate of change of, in this case, the z value in that direction. Okay, so this is the idea. We're going to measure with the direction derivative. So if you think about it, what we're going to be doing is like intersecting this surface with a plane. Think of something like this. So you can have a curve up here, and what you're measuring is the rate of change as you move along that direction. So it's like the tangent in this direction, the slope of that curve up here. Okay. Now, before we get to that, I want to say that we already did this. That's why I copied that before. So let me paste it here. We already did this in the case of a partial derivative. When I did the partial, or when you learned the partial derivative, let's say with respect to x, you kept y constant and move in the x direction. So we were thinking this as you move, it's the same situation, but you're moving in this direction, in the x direction. So you move in the direction of the unit vector u, which is the 1, 0. We did this with a plane up here. Oops, it's the wrong place that overlaps that. So we see a curve over here. And oops, that should go through that point. And let's make this curve make through that point. Make this curve go through that. Oh, sorry. Let's pretend this curve goes through the point like that. And then what I'm measuring is the tangent in that direction from this point. So what is the partial derivative with math? What this means is the partial derivative of f with respect to x was really a limit when somebody goes to 0 of f evaluated at the point plus t times my e1 vector. E1 is the 1, 0, or the u. That's what I'm using here for u. Then minus f of x, the point, divided by t. Right? So I'm measuring what is the value of the function at this point, what is it at a nearby point, subtract those two values, divide by t, it's the difference quotient as in Calc 1, only that you're adding, the point here is that you're adding a multiple of u1 to the vector x. So you move from this point AB to a point over here. And you take the limit when t goes to 0. So in practice, if you do this with coordinates, this becomes, I don't know how much I want to keep going this, but this becomes the limit when t goes to 0. If x, remember, x, this is my point x, is AB. So when I do this, I get x plus te1 is really f at a, which is the coordinate of x, plus t, comma b, because te1 is just t comma 0. So you're adding the t0 with the ab, right? And you get minus f of a comma b. And then in the limit, this becomes the derivative of the only treating the x like your variable and keeping the b as a constant, and you evaluate this, and it makes perfect sense. That's a partial derivative. So now I'm going to do the same thing in this context for any direction u. So let's move this a little bit to the side. So now my notation for the derivative, I'm going to call it the directional derivative, the directional derivative in the direction of u of my function f is going to be the same thing as before. This is my value x, and then I'm going to have my vector, my unit vector u in some certain direction. Okay. So now I'm really going to be like interested in this with a vector, with a plane in the direction of u up here, and you're going to see a curve somehow like that. I'm trying to measure here. So I'm going to find at the x point, at the x plus t times u point, evaluate up here, subtract, and find a difference quotient. So this would be the limit when t goes to 0 of f of the same as before, x, the point x plus t times my vector u now, we put vectors here, minus f of x divided by g. Now I'm going to treat this a little bit differently. I'm going to use the fact that I'm going to think of a curve gamma of t, which is really the line that goes through to point x in the direction of u. So I want this to be this line. Okay. So gamma of t is nothing but the point AB plus t times the vector u, which is the, I had coordinates for u, let's call it u to be h comma k. And this is a unit vector. We need to make it a unit vector so the magnitude doesn't affect what we're doing. So we uniformize this by making unit vectors. So gamma of t is this red line in arrow 2. So this is really a plus th, gamma plus tb, sorry, b plus tb. I don't think I really need to write like that, but b plus tk, sorry. Okay. Now, notice that if I do this here, what I'm measuring over here, when I did this is really, I can think of this f of x plus tu is finding a point nearby here, and then minus f of x is here. This is exactly the same as finding x of x plus tu. This is gamma, right? X is a b plus t times u, which is this. This is x plus t u. So I can write this up here really like the limit when t goes to 0 of f of gamma minus f of x. Or let me put that 0. Right? When gamma, sorry, not 0, gamma of 0. Because gamma of 0 is the point x. So sorry, I didn't follow the colors there. But this really looks like the derivative of f of gamma. This is the definition of derivative of f of gamma. Right? At the point 0. At t equals 0. It's 0 plus t minus gamma of 0 divided by t. Now, in a previous video, this is why I said we needed that. We saw that this is a composition of a curve gamma with a function f. So this really just becomes, this is what we saw, the gradient of f dot gamma prime. All these evaluated at the point. I'm going to forget that for a minute. Because what I want to get to is who is gamma prime? Well, if you get it from here, gamma prime is really just the point x again. Or sorry, gamma prime is the vector u, because this part is constant. If you can either from either way, gamma prime of t, you can see from up here or from up here, it's going to be h comma k, which is the vector u again. So it's just gradient of f dot u. So that's what we want to get to. Okay? So the directional derivative of a function f in the direction of u, all we need to do is find a unit vector in the direction of u, take the dot product of that unit vector with the gradient of f evaluated at the point, and that is the directional derivative. So it's a shortcut to find it. It's a very nice way. And in the special case where the direction u is one of the coordinate axes, it becomes the partial derivative. And that's clear because if u is, say, the 1, 0, then of course the directional derivative of u in that direction is just, you can do the partial f, partial x, partial f, partial y, dot the 1, 0, which of course is just the partial of f with respect to x. So you recover that idea. Okay, one last thing I want to touch on this is this. There's our message df right there. So we got this expression for the directional derivative. It's the gradient of f dot the unit vector u. Because remember that the dot product becomes the magnitude of one vector, magnitude of the other, and cosine of the angle between the two vectors. So because u was a unit vector, we can disappear. We can forget about that term, and it's just the gradient of f dot, times the cosine of the angle. Who is the angle? The angle is between the gradient and the unit vector. Okay? The gradient of f evaluated at the point is a fixed vector, and then this is the angle of that one with the direction in which I'm measuring the directional derivative. So the question here is, when is this max? When is this maximum? Well, the u disappeared, but the u is there, okay? And the u gives you a direction. It's not disappearing because the direction of u is embedded in here, the angle, okay? So if you have if I have a function and I have a surface up here, what I'm saying is I can grab at a point, I can find different possible vectors used, that way or that one or this one. Okay? Each one of those gives me a different value for the angle theta. Okay? Because this one is fixed. Once you find the gradient of f at the point, that one is fixed. So in which direction is this a maximum? Well, the maximum would be when the maximum of the cosine value could be the maximum, and the cosine is maximum when the theta is 0. because the cosine is 1. So when is this the maximum? When u, the vector u, is parallel to the gradient. Which is saying, another way to say this is, at each point here, the gradient is pointing in the direction at which the direction derivative is the maximum, which is the direction at which the z function increases the most. So a very simple example for that is if you have the function f of xy equals x squared plus y squared, its gradient is 2x comma 2y. So the gradient at each point is this vector field that's going outside, right? At each point, you have these vectors going outside. It's the same. And what's happening is that if you see it in 3D, this surface looks like this. Surface, x squared plus y squared. And at each point, the gradient is pointing outside, which is the direction at which you will increase the most if you follow that direction on the surface. This is an explanation of why the gradient is pointing in the direction of maximum increase of the function f.